All right, so this is 47-17-4 lecture. It's a starting lecture for the section 3 for analyzing the text data or the 1D sequential data, because in this section we will talk like naive Bayes model, Bayesian classifier, and there's a lot of probability proportion there. So this is the slides to students who need a little bit review about probability. And most of the lecture here are the recordings from my last year. All right, split the whole video into two parts. The first part is about random variable, and the second part is about these three important probability calculation: joint probability, marginal, and conditional. And how do you calculate it? Will be a concrete example. How do you apply those rules to calculate interesting like a joint probability or marginal probability or conditional probability? All right, so
I want to cover some basics about type of probability we normally care. So they're only through, so whenever you think about probability modeling, don't worry about those. There are a lot of terminologies because this is a really big discipline, research discipline, and it's science field. So everything that you learn, try to anchor them into three things. The first thing is it's either a joint probability, or it's marginal probability, or it's conditional probability. No matter how complicated all those behind the model are, and they're just it's about one of the three. So if what you care is a joint probability, and it's hard to estimate directly from data, and people just use chain rule. I hope you remember what is chain rule. So if you care, you want to estimate joint probability, it's not directly countable from your data. It's hard to directly count those from data, and you use chain rule to estimate it. So I'm going to give you an example later, so remember that. If what you care is a marginal probability, and you can directly estimate it from data, directly assuming just do counting, you can't do the counting directly. And you normally use something called the total law of probability, which I already introduced in the previous slides, which I'm going to cover. What if you care is a conditional probability, and you can't count it from the data, you're going to use Bayes rule. And this is everything you need to memorize. And this is almost like the rule. Just memorize that, then all those complicated model or a lot of different formulations all follows just this generic three thumb of rules. So, but what are these rules, right? So, what is joint probability? Joint probability is just multiple random variables. I want to estimate the probability of multiple random variables, or multiple events all together, that joint probability. And so, yeah, this is a little, this page is not precisely clear. So joint probability is like, I want to estimate P and B. Marginal probability is, I want to estimate O link B or O link A. And conditional probability is, I want to estimate either A given B or B given A. So for joint probability, I said chain rule. And chain rule is pretty easy. If it's easier to estimate PB directly from data, I'm just estimating PB first. And then do P a condition on B. So this is what I meant chain rule. So assuming PB and PA condition on B can be directly countable from data, and this multiplication will give me the drawing probability of P, A, and B. Then let's see the marginal probability. The marginal probability is, we normally use that PB and A plus P, B, and not A. So if directly estimating PB is hard, I'm going to make use of, this is called the total law of probability. If you remember PB, this, you can even derive this very easily. So why is this? Is because PB equivalent to and O is my sample space. And it's an AND relationship. And this equivalent to A and not A. And because they are disjoint operations on the sample space, which I already proved before. So feel free to check out that page. I did derivation, and then that's the reason why you can derive this. Yeah. So if this is because maybe PB and A are easier countable, and PB and not A are easier countable. So I'm using this total law of probability to estimate marginal. All right? So now let's look at conditional probability. So assuming I'm trying to estimate PB conditional A, it's not directly countable. I'm using Bayes' rule. So who still remember what is Bayes' rule? PB conditional A, how can I estimate PB conditional A? So let's actually just use the you can get this, right? All right. So because, because P, B, and A, it's hard to directly estimate from data. So if P, A given B is B, and this is normally what you learn, I think, from about the way of how Bayes' rule is introduced. But this all sounds like just a reformulation of this, right? It's nothing special at all. It's a reformulation of this and plus this. All right, so let's go to see an example. So I'm going to skip a lot of this because I cover quickly and you should read by yourself. All right, so let me make an example now. Assuming this, we are given a dark box with 3 red balls and 1 blue ball, which makes the RRRB. So what is the probability of drawing 2 red balls in the first 2 tries? How do I directly count the first ball is red, the second ball is red too? If I want to use direct counting, I have to just lay out all the possible first 2 try, and then count how many RR is in the all possible try, and that's the way you get it, right? It's actually relatively difficult because there are 3 red R. It's hard to distinguish a lot of RR. But it's much easier to decompose this into a chain rule based formulation is, so there are 3 things I care, right? So let's count the first. Let's do the first. So what should be the second factor in this multiplication? Okay, so what is this? So the first try is a red ball, second try is a red ball. I decompose it using the chain rule because it's not that easy to directly count it, but it's so much easier to do these two numbers. So what is the probability of the first try, the first draw, is a red ball? You should even learn this in your high school, I think. What's the probability of the first try is a red ball out of the RRB? Yes. This is 3/4. And then what is the second term? Conditional on the first try, the first draw is a red ball. What is my second try? 2/3. This gives me 1/2, which is really easy to do the calculation, right? Because the first try, there's nothing conditional on, and it's really just counting. There are 3 red balls. Sure?
Here, part of the question should specify if you're doing this with or without replacement, right?
Yes, good question. We don't put it back. We do not put the first, if I draw the ball, I'm not going to put it back to do the second ball. Yeah, you're going to put it aside. Yeah. All right, so let's see. What's the, this is a joint probability, right? And this is a marginal probability. What is my second try is a red ball? How do I calculate this? Can I directly count it? Just do counting. What's the probability, the marginal probability, the second try is a red ball? Conditional on nothing. How to calculate this? All right, so let's go back to what I just said. Let's use this called total law of probability. How do you, if directly calculating marginal is hard, I'm going to make use of an extra variable, and by count the intercept and case of my interested variable, and every possible values of that extra variable, which in our case is what? It's B1, right? So this really is B1 equals to the R, B2 equals to the R, plus B1 equals to the B, because there's no other possibility at all. And you can use what we have from the first, and then do the calculation of this 2, and you can do the calculation of B2 equals to R. So this is what I meant to use total law of probability to estimate the marginal probability. When this marginal is not directly can be easily estimated from the data. All right, and then the last case. So the last case is, I want to know what's the probability my first try is a red ball, conditional on my second try is a red ball. And how do you write out this? This is actually pretty complicated if you want to lay out all the possibilities, then condition on the B2 is red, and to count how many times the first is red too. You can do that by just doing the brute force enumeration of all the possible outcomes. And this can be, you can just use, clearly, just I said, base rule. This equivalent to B1 equals to red, B2 equals to red, over B2 equals to red, which is exactly the first and the second. You just estimate it. And this is actually the base rule to estimate a conditional probability. So more concretely, I showed you, so this is, we just calculated. Oh God, why did I write? Red? That's so weird. Yeah. Oh yes, it's correct. Okay, it's correct. I did correct. Okay. So 3/4. Yeah, I was trying to show B1 equals to B. The black ball is 1/4. And this part is 2/3, and then this is 1/2. And this is the marginal probability. You do B2 equals to R and non-conditional joint with B1 equals to R, B1 equals to B. And then it's, because this is joint probability, similar to the first we did, then you use chain rules to decompose this B1 times B2 condition on B1. This is the first try is red, and this is the first try is black, and then it's very easily, it's, in this case, B1 equals to B is 1/4. So when the first try is black, and then the second try is red, is probability. Because when your first draw, you already got the black ball, and then the second ball absolutely will be red. So that's why this probability is 1. So this is the marginal probability PB2 equals to red. Okay, question about this? These 3 examples give you a real nice intuitive way to use the rules. And also why. Why do we use the rules? Question about this? All right, so, and then the last one is that harder conditional probability. It's PB1 equals to R, condition on PB2 equals to red. And then because it's much easier to do the calculation of B2, condition on B1, so we're making use of base rule to get the joint probability in the denominator, and then the denominator is the marginal probability, and this marginal probability is also hard to do the calculation. That's why you use the law, the total law of probability, and then you decompose it with this both the B1 equal to R and B1 equal to B case, which is this page. So kind of memorize. So what is P B2 equals to R? It's in the denominator. In fact, it's a decomposition of B1 equal to R, B2 condition on B1, B1 equal to B, B2 condition on B1. Let's look at this. This upper denominator is B2 equals to R, condition on B1 equal to R, and the denominator is, put the previous page here, so I want to show you the full thing because this is the most classic way to use base rule. So this is you're using the marginal distribution decomposition to write it into two sum, and then you use the chain rule to decompose them into product to calculate that drum probability. So in the end, you can tell it's all those similar chain rule, right? You just use the chain rule, or you use total law of probability. That's the only thing you use, and all the things here, it's just reformulation or reuse, a different form of using that two rules. Okay, question of this is extremely important. Just to let you know, extremely important. Who has question about the denominator? Yeah, so this is just chain rule, and then this is just total law of probability, and then use chain rule to apply on this drum probability, and then you get how to directly estimate each of those from data, and you get this difficult to estimate conditional probability from the data. All right, so I already used the base rule, but yeah, so here it is just PB conditional A equals to PA and B over PA. You can use chain rules to decompose PA conditional B times PB and over PA. And then you can just decompose PA even more. So again, so why do we even use this all those reformulation? Because so some quantities is easier to estimate from data directly, some quantities are harder. And the whole thing is making use of those easier estimated quantities to calculate those harder to estimate quantities. No other reasons. Or later, we're going to do classification, and then you're going to, so assuming later we're going to use maybe what we care is Py given X. And this is exactly classification we try to estimate, right? So in the classification case, your Y variable is a discrete variable. And they're assuming it's binary, there are only two cases. So is P yes or P no, so how do you get this? So if I know Py equals to yes, conditional X versus Py equals to no, conditional X, if this is larger, I'm going to predict my X into yes. So, but how do you directly estimate Py equals to yes, conditional X, right? And there are all variation of different classifiers. So that's how do you model Y conditional X? And then the different algorithms provide you different ways. So there's some method directly estimating Y conditional X as a function, some kind of function. And there's some other method using base rules to estimate Px X conditional on Y equals to yes over Px. And the lower is similar. Px conditional on y equals to nil over px. So this type of, and then compare. So then we're going to, y predict is yes. And this is exactly the philosophy behind generative-based classifier. So generative-based classifier trying to estimate x conditional on each class possible output. And this is generative classifier, and there are also discriminative classifiers is they don't use base rules to directly estimate px conditional y, but they are directly estimating py conditional x from data directly, and this type of model called discriminative model. So you can tell it's everything about conditional or marginal, right? There's nothing fancy at all. I mean, if you ever heard about generative classifier versus discriminative classifier, the only differences is what type of conditional you're modeling. Do you directly modeling y given x, or you're modeling x given y? And even though so those type of base class generative classifier, they're using modeling x given y, but they have to again convert it into y given x because that's the decision, the scoring you have to rely on in the end is my conditional probability y have a specific values is the largest over all the possible y conditional on x. So we're going to cover that next class, but just I want to give you a flavor. Why do we even learn or review base rule? Why do this even matter? So it's again, it's about what marginal you model from data. Yeah, there should be a y equal to yes there. Yeah. Yes, totally. Thank you. Yeah, it's a little tight. Sorry, just. Yeah, of course. It's the chain rule. Yes. All right. So, and then there's all this variation of base rule. If you look at this is exactly the one we just used to estimate PB equals to the second try is the red, condition on the first try is red. So the upper is the second over the first, and the lower is second over the first choice, and second over the second choice. Let me just re-emphasize this again and again because this is it's B1 red over the other way. And B2 red over and B1 red and over B2 red, B1 red, plus B2 red and B1 black. So this is exactly using this. And you can have even more complicated if there are so many possible choices in the first, the one you condition on. So, so next I'm going to show you, so this is also that. So more concrete values, and then you decompose this marginal using the total loss probability when you have not just two cases, but k cases. So this is like the total decay of x equal to k. You have to calculate that joint probability with the y equal to yj, coupled with x equal to x1, x2, onto xk. And so now, so quickly is, so what we normally see is not this. In fact, what we normally see is something like this. It's a smaller x conditioned on a smaller y. Excuse me. Y. Yeah. So what you normally see, the base rule actually is the smaller x conditioned on smaller y. So it's just a simplified version. It simplified all those random variables out. But you have to actually, these are two different random variables. And here is x equal to x, y to y. You simplify them using only the values of x and values of y to put in those type of joint probability or marginal probability. Don't get confused. And always, there's event. There's really a series of concepts, right? So the first concept is it's about event. It's a subset of sample space. And you simplify it into x equal to x into a functional view. Then you even simplify that, forgetting about that function capital variable. You only lift the output value into this probability. But keep in mind, it's actually a random variable, and this represents two different random variables. So in this case, sometimes, so this actually represents what? This represents two random variables. So assuming the first random variable is a weather, the second random variable is like grass. So don't get confused, and can we put rain and wet together as the output value of one random variable? Just keep in mind, whenever this means two different random variables. Yeah. So you can even have like two random variables in the conditioning, and this is the base rule when you have two random variables. So it's actually more complicated. So yeah, and then in the marginal distribution case, we always write something like px equals to summation yz, px yz. So also don't get confused. Here it's about two different random variables, y equals to smaller y, capital Z equal to smaller z, and this normally represents two layers of 4 summation. So there are a lot of simplification in a lot of probabilistic modeling, and be very, very careful when you read those. So in the end, just is this conditional joint? How many joints? How many are conditional on? Which one is the marginal? And be mindful when you read and also when you write this type of formulations. These are all. Just feel free to read those. And then the last one is about independence and conditional independence. So x and y are independent if and only if. So the joint probability equivalent to the multiplication of the marginal. So this is a sufficient and necessary condition. And what it has a different formulation is, so if and only if the joint probability equals the 2 multiplication, or the joint probability or the conditional probability equals the marginal. So these three views are equivalent to each other. If px conditional on y equals to bx conditional on x, it's also a necessary and sufficient condition. And this is also a different view of necessary and sufficient condition. Yeah, so, okay, and then I think everything here. So, okay, so there's a third thing is this formulation. Sometimes, actually the majority of the time, when people write as, one variable is conditioned, it's independent with another random variable, you have to translated is it's into, this means this sufficient and necessary condition holds for all the possible values of xi and yj. So this is also very important. Whenever you see this formulation, which means this random variable is independent from another random variable, it means for all the possible xi and yj, and this sufficient and necessary condition all holds. So they should, just for all the possible values, this function holds. So this is about independent random variables. Now let's move on to conditional random variables. So conditional independence is represented by this formulation. So px and y, px equal to x, y equals to y, condition on the z, equivalent to the conditional, actually this is a joint and conditional, equivalent to two conditional multiplied together. If we write, you can write it more like a graph. Z variable so this relationship is completely reflected in this graph. So the z variable is the parent of x and y, which means one after, so the value of x doesn't tell you additional information about y when given the z. Yeah. So when given the z, these two are independent. However, this doesn't mean x and y are independent. So this is called conditional independence. They are independent to each other when conditioned on the z variable. So why do I care this? So one of the most important algorithm we're going to learn later is something called, this is just a more concrete view, and then, so just a summary. Independence does not imply conditional independence, and conditional independence doesn't imply independence. So why do I care about the conditional independence, which is this? So when I have the y variable, there's many models. There's a group of models called naive Bayes classifier, which is this. So I have p different random variables, right? It's each one of my features. So it's called a naive Bayes classifier. I can assume all the feature variables are conditionally independent from each other when given the y variable. So this is a very classic generative model called a naive Bayes classifier, which you're going to implement in the homework 5. And there's a reason why I'm assuming this. So in the end, this is assumption. It's assumption you're assuming on your model. So similar to what we had before, I'm assuming my model, a linear regression model, which means my y and my x is a linear relation with a linear relationship. Or I'm assuming my x and y is nonlinear, or polynomial 2, polynomial 3, polynomial 4. In this type of probabilistic model, it's the same thing. You assume, you're making assumptions about the model. Similar to the regression, all those cases, what is the polynomial line? Here is, what's the relationship among the features and to contribute to the y? So here, my assumption is there's no dependency relationship among features when I'm conditional y, and this is my assumption, which makes what? This is almost the simplest generative type of probabilistic model, modeling the classification. So we always start from simple case, then go to complicated case, right? And this is the simplest case when we use generative model to model our data. And of course, later you can have much more complicated model, how do the x and xi related to each other, and much more complicated model. It's much more complex compared to this model I show you, and they are conditionally independent one given the y. Okay, I think that's it.